Have you ever tried fine-tuning large language models? And if so, did it feel like this? In other words, did you feel overwhelmed by all of the unexplained knobs that you could tune? Well, Tulu 3 is a model from the Allen Institute of Artificial Intelligence in Seattle that is addressing exactly this problem. Compared to other open weights models like Llama or DeepSeek, Tulu 3 is fully open source. That means, in addition to the standard paper and model artifacts, they also released all of their datasets and all the code to train, evaluate, and even set up infrastructure. They're basically taking the guessing work out of fine tuning, and they're helping you draw that owl one step at a time. So, if you're tired of fine tuning based on vibes, then stick around. First, here's a quick reminder of how LLMs are trained nowadays. We start with a randomly initialized model that is completely incapable of making any sort of predictions. Then we run pre training by predicting the next token on the entirety of the internet. Implicitly, the base model ends up acquiring a lot of world knowledge, but it's not quite usable yet as an assistant. It has an inconvenient API where it just finishes your sentence and builds on top of it. To make it more conversational and infuse other desired behaviors like safety, we do post training. This is a step that is generally poorly documented even in open source projects like Llama. Just the other day, I was trying to fine tune a Llama 3.2 model on a public dataset, and I was getting very frustrated because, according to Meta's report, I should be seeing a 2% increase in accuracy compared to the base model, but it just seemed impossible to reproduce. And I found out I wasn't the only one facing this problem. Mr. or Mrs. Ketchup 123 here made me feel understood. They said, I have spent a week optimizing hyperparameters but never seem to obtain satisfactory results. I have trained LLMs before, so this really frustrates me at this point. 203 addresses exactly this pain point by offering a lot of transparency around the post training process. We're talking methodology, hyperparameters, and code. So let's discuss Tulu 3's post-training recipe. They start from a Llama 3.1 base model, but the recipe is agnostic to the specific base model, so you can plug in your preferred one. Post-training consists of 3 stages, and we'll talk about them in turn. For each stage, we'll cover 2 dimensions: the training data and the training methodology, or the learning objective. The very first step is instruction fine-tuning. Its goal is to change the base model's behavior away from simply finishing a sentence towards a more assistant like experience where it responds to instructions. So naturally, we need to train it on instruction response pairs. The 2 to 3 pipeline gathers data from 2 sources. First, they reuse existing public datasets, and second, they generate synthetic data. This hybrid approach is what gives the model its name, since Tulu is a hybrid type of camel. We'll get to the synthetic data later, but first let's take a peek at some of the existing public datasets. The AI2 team published this really neat spreadsheet with all of the public datasets that they used, and it's a great resource if you're on the hunt for fine-tuning or evaluation datasets. And since we're talking about instruction fine-tuning, let's look at one of these datasets. This one looks like a coding one where we're given a problem, which is the instruction, and a solution, which is the reference response. Here, the reference response is actual code like C++, Python, and so on. Anyway, this is just one of the datasets. They used a ton of them. But how exactly do we leverage these instruction response pairs to fine-tune the model? Well, we still use the next token prediction task, just like for pre-training. We just need a way to concatenate the instruction and response into a single piece of text. Looking at their GitHub repo, I found their chat template, which is just a recipe for how to flatten a conversation. So you can see here that they're concatenating the system message, user message, and assistant messages. Interestingly, it turned out that models are actually quite sensitive to the specifics of the chat template. For instance, they show that if they replace this very last new line with an end of sentence token, the performance of the model is boosted, which is kind of sad news because it means that fine tuning is pretty brittle, which goes to show that it's really important to publish all of these nitty gritty details. Okay, so Once we structure the data as flat conversations, we can fine-tune the model with the next token prediction task. This step is considered supervised, and that's where the SFT suffix in the model name comes from. My type A personality has to intervene a little bit and complain about terminology here. Note that both pre-training and instruction fine-tuning are using the same learning objective, basically next token prediction with cross-entropy loss. However, one of them is considered unsupervised and the other one is considered supervised. Presumably, pre-training is unsupervised because it kind of discovers world knowledge on its own without us telling it explicitly what it should remember. And presumably, instruction fine-tuning is supervised because the reference response is in the text that we're training on. It kind of makes sense, but not all the way. I guess we'll just have to live with this inconsistency. Okay, the second post-training step is preference fine-tuning. If you've ever used ChatGPT, you might have seen the screen that invites you to pick between two model responses. That's because OpenAI is using your free labor basically to gather training data for preference fine-tuning. So for this step, we need an instruction, two responses, and a human preference between option 1 and option 2. Out of curiosity, let's take a look at the public datasets that are used for preference fine-tuning. For instance, alpaca farm human preferences. Okay, so we have an instruction and input, which I assume they will get concatenated to form the final instruction, and two alternative outputs together with a human preference. Again, this is just one of the many preference fine-tuning datasets that they used. The objective is to teach the model to do pairwise ranking, or in other words, to rank the two responses. The training algorithm is called Direct Preference Optimization, or DPO for short. Again, this is where the suffix in the intermediate model name comes from. Let's talk about DPO. We start with the checkpoint from the previous stage, so Tülu 3 SFT, and during one training step, we feed the instruction into this model. Ultimately, an LLM is a statistical machine. For a particular instruction, it can give you the probability for any possible response or any combination of output tokens. That's why we can interrogate it and figure out what probabilities it assigns to the two responses in our training data. Now, we can check whether the response ranking from the model agrees with a human preference. For the sake of argument, say that humans prefer response number 1 for this instruction. In DPO terminology, response number 1 is correct and response number 2 is rejected. DPO aims to maximize the probability of the correct response and minimize the probability of the rejected one. So the loss is the negation of that. And once we compute the loss, we can do backpropagation to update the model weights in a way that will favor the correct response. An interesting discussion point is the provenance of the responses we rank. In the public dataset we looked at, the responses came from some external LLM, maybe GPT-4. That's why these are called off-policy responses, because they come from an external policy. And in this context, the word policy is just synonymous with LLM. And this is not ideal. We want to align the current model with human preferences, so it would make more sense to actually rank responses that come from this model, Tülu 3 SFT. Let's see what DPO with on-policy responses would look like. Just as before, we feed an instruction into this model, but this time, we sample two responses from Tülu 3 SFT and keep track of their probabilities. Since these are freshly generated responses, we don't know the human preference. So we'll just use an external LLM judge like GPT-4o to guess this preference. And from here, we continue just like we did for off-policy DPO. In practice, the authors of Tülu 3 ended up using a mixture of off-policy and on-policy DPO. Finally, we've reached the last stage, reasoning fine-tuning, which leads us to the final Tülu 3 model. This is a reinforcement learning step on tasks that have verifiable responses. That includes math, computer science, or logic. So given a model response, we can deterministically compute a reward, since math is pretty ruthless. You either get it right or you get it wrong. Let's see how training goes for this final step. Again, we start from the previous checkpoint, in this case, Tülu 3 DPO. We feed an instruction and we get a model response. And we deterministically compute a reward, which is 1 for correct answers and 0 for wrong ones. The reward is basically our training signal. To backpropagate it, The authors use an already established method called proximal policy optimization, or PPO for short. I'm glossing over the details of PPO because it's one of the more complicated parts of machine learning. But if you like math and derivations, I'll do it. Just let me know in the comments. I do want to mention that this is very computationally expensive, partly because there are two additional models that need to be trained as part of PPO. A reward model, which estimates rewards at the token level instead of full response level, and a value function, which intuitively estimates how hard the current instruction is and therefore how much of the reward we should be taking credit for. So that's a Tülu 3 post-training recipe. But I want to go back and briefly talk about the training data. If we learned anything from DeepSeek, the Chinese model that disrupted the US economy for a while, is that we need a lot of fine-tuning data, somewhere in the ballpark of 1 million. And public data sets alone can't get us there, so we need synthetic data. These three stages require different data formats, but the common denominator is that we need instructions for all of them. This is why LLM model providers are so desperate to have you use their chatbots, because they need the prompts to keep making their models better. You might be tempted to think that generating instructions is as trivial as asking GPT-4o to come up with a bunch of things that humans might ask. But that's actually tricky at this scale. GPT-4o doesn't have enough imagination to generate hundreds of thousands of different prompts. It will start repeating them after a while. And this is academically known as mode collapse. Instead, Tulu 3 leverages this paper, which advocates for creating personas first, like a moving company driver or a chemical kinetics researcher, and then for each persona, prompting the model with 2 or 3 variations, like a math problem or a logical reasoning problem. With this method, given that there are 1 billion personas, we could in theory get 3 billion prompts. Once we have the instructions, we can simply generate the responses with GPT-4o because answering a question requires less imagination than coming up with it in the first place. Before wrapping up this training data chapter, I wanted to mention one more important effort that shows the rigor of this project. They made sure to decontaminate the instructions. They removed any prompts from the training set that had any overlap with the evaluation set, to make sure that the evaluation set remains fully unseen during training. The final evaluation shows that each consecutive step in the post-training pipeline improves performance. These numbers are averaged across all evaluation benchmarks, including knowledge, reasoning, math, coding, and so on. Tulu 3 is competitive to other open source models, including Llama 3.1 Instruct and DeepSeek v3. Note, however, that this comparison is against older versions of Llama, which is currently at version 3.3, and of DeepSeek. So this is not the R1 model that was in the press recently. It's also interesting to see that these models are still behind proprietary ones, but they're putting up a good fight. So this was an overview of Tulu 3's post-training pipeline. With this base knowledge, you can go ahead and fork their code and fine-tune your LLM in a principled way. I really think this is much more productive than taking Colab notebooks that simply use maybe the SFT trainer from the Transformers library with some random hyperparameters and then run one inference step and never prove that the fine-tuned model is better than the base one. One more thing before I go. I have no idea who's watching these videos, so if you've made it so far, please let me know in the comments who you are, what you do, and what kind of content you'd like to see. I'll see you in the next one.